I can start recording. I can plug the little mouse thing in here so I can stand in the back and click. Really my ultimate desire. Yep. All right. So we'll get going. Good morning. Hope everybody's well. Another beautiful day here in Vancouver. At least it's not snowing or minus 40. Minus 40 being my favorite temperature because you don't have to specify whether it's Fahrenheit or Celsius because it's the same number. It also happens to be the freezing point of ethanol. If you have a cheap thermometer, like an outdoor thermometer, they'd stop working. Most of them stop working at minus 40 because the only way you can actually have it work below minus 40 is to use something that doesn't freeze at minus 40. So keep that in mind. Don't leave your Everclear outside when it's below minus 40 or it will be frozen and you won't be able to drink it. Not without warming it up. Important things. Let's talk about logistics. This is going to get shorter because there's less to talk about. You'll notice the list is smaller and smaller. Next Monday is the Project 3 due date. As I was commenting before class, I assume that people are waiting until Monday afternoon, probably around 7:30 p.m. to start it. That's all right. As I usually tell people, I take the last 48 hours of the project off. So good luck. I would recommend, if you haven't at least looked at it, to try and look at it a little bit. Project 4 is then released for the 13th of March. I am assuming that no one will be working on Project 4 until after reading break, because reading break is usually not about reading, but about not doing anything related to school. Which is kind of sad, because I'm excited because I actually have this whole plan of doing research over reading break. So, interesting. I've gotten all excited about using ChatGPT as a interesting front end to this back end stuff that I'm trying to build to make it easier for you to find random data that you've created and scattered across a half dozen different locations. And so while that looks like it's a month away, you're probably not going to start working on it next week because you'll have just finished Project 3 and you'll be moving your attention to something else that's pressing. Then you won't work on it the week of reading break. And so what that really means is you'll have about 2 weeks. Do not wait till the last minute on that project. It will kill you. Project 4 is Paxos. And I will be talking about Paxos next week. And I'm trying to lay some of the groundwork for Paxos today. Project 5, still far enough off in the future, I don't expect anybody will be looking at it for a while, but you're welcome to. People who are in the alternative paths, and there are 15 people in the class who've chosen to do this. We're having conversations back and forth. When I wrote the slides yesterday afternoon, there were a number of people who had outstanding questions. I think most people have addressed them since then, but feel free to keep chattering if you are in one of those groups. And if you're not, you don't have to worry about that. You can just keep doing. One person is doing the Path 2 stuff, and I was excited to see that they posted a link to their first PR. So it was very small, which is exactly what you would expect for your first PR in a public open source project, but it was cool to see that. Let's see. So I did do Zoom hours on Tuesday. I saw that somebody popped in around like 10 minutes before the end of the period, and I had given up about 35 minutes after the start because there's just something weird about sitting on Zoom smiling. So if you plan on coming to office hours and you don't think you're going to make it in the first half and you plan on coming in the second half, give me a message or something, message me on Discord or, I don't know, Piazza or whatever your favorite communications mechanism is. I did do a discussion because, of course, I can at least talk into an empty room full of no people and record it. And that has been posted on Piazza. There's a link to the recording of that. I talked about Project 3. Oh, and of course, there will be casual office hours this afternoon. That's just on Discord. You can pop in and do voice only or voice video, screen share. We've had people do that as well. And if nobody's there, I'm sure I'll find something else to do. I can go pick flowers. I'll start up World of Warcraft and fly around and pick flowers. Or go kill things. Very relaxing to kill pixels. Oops, what happened here? That's broken. There we go. Okay. Well, apparently I didn't edit that quite right. I'll fix that. Yes, so in fact, I do want you to read Gifford's paper. It's actually not too bad, and that's a lot of what I'm going to be talking about here. This is a late 1970s paper. Gifford was a PhD student at the time at Stanford University, and subsequent to that, he became, and he still is, as far as I know, a full professor at MIT. I'm kind of hoping that I can get my PhD done and use him as the external examiner, actually, because there's a lot of overlap in what he did, not this, but later, and what I'm doing. And Margot knows him, because Margot knows everyone. I do recommend that you actually look at Kleppmann's notes. All of his notes are actually quite useful. So if you're finding that you're struggling with some of the material or you have deeper questions, you want to look at a different perspective, because that can often be useful. Kleppmann's notes are good. In this particular case, I'm suggesting it's a relatively short section, section 5.2, and he talks about distributed systems. I'm going to be talking about crumbling walls here. That is actually a link to the published paper. I've gotten a very pretty version of it. It's much more readable than the one that I've been using for many years. But it's what I'm going to be talking about today. And mostly it is a theory paper about building quorum consensus protocols. And what's interesting about it is that it doesn't require a majority. And most of the actual consensus algorithms you see will require a majority. Some of them will require supermajorities. I've seen some blockchain consensus algorithms that require supermajorities because it makes things more Byzantine resistant. Anybody have any questions? Anybody awake? I see a couple of hands there. So we've got 4 people who are awake and the rest of you who are still going, why am I here? Why didn't I just stay in bed and watch this on Twitch, which really means sleep? Any funny stories? All right. I picked a slightly different failure today. And part of the reason I picked the slightly different failure is because it provides some insight into why these things called key value stores are so important. This entire University of Washington lab stuff, the DS labs that the projects are based on, is building a sharded key value store. Why? In 2004, before Amazon Web Services actually existed, Amazon had a meltdown on their actual website. Amazon.com, Amazon.ca, Amazon.co.uk, so on and so forth, where literally for about 2 weeks, things were really screwed off. For a while, it was completely inaccessible. You couldn't actually get to the web page at all. And much of what they realized was that their IT infrastructure was essential to their actual business. Now, of course, we live in a world 19 years later where Amazon Web Services is the moneymaker for Amazon. It's not the revenue generator. In fact, the sales part, the front-end retail sales part is still what generates the bulk of the money that comes into Amazon, but almost all that money goes back out. The money that people pay them for providing distributed system services, everything we are talking about in this class, they get to keep a lot of that. And Amazon is profitable largely because of AWS. But their original motivation for doing this was because they found that their own business relied upon their IT infrastructure services to a critical level, to such an extent that an outage of 2 weeks during their highest sales season, highest sale period of the year, was crippling. And they survived it, but it was really, really rough. Amazon Web Services didn't exist in November 2004. This was partial motivation. One of the things they found was that they had a scaling issue, that when they started experiencing high load, everything melted down. One of the key elements that melted down was their use of traditional databases. And so they said, what we really need is we need something that is as effective as a database, but is much more scalable. And that is a key value store. What a key value store does, it has a blob of data and a value we use to look up that data, the key. That's it. That's all it is. And I come from a background, I'm a file systems person. I come from a background of building things on top of key value stores. We didn't call them key value stores, but that's actually exactly what they are. All modern physical file systems are built as an array, potentially sparse, of entries. And we find the stuff we're looking for by going to that location in the table and pulling it out. That's what a key value store is. That's it. It's just an array. Now, the key isn't necessary. Now, it's not necessarily a linear array. That's the interesting part about this, right? It's an associative array. So the key is that I take that name you give me, the key, and I go look it up, and I pull the data back out of it. That's all. It's super simple. We can give it very simple semantics. We can, in fact, boil it down to exactly 3 operations. Get, look up that value by this key. Put, write this value using this key. If there's already something there under that key, replace it or fail it. You can do either one. And delete. I don't want that anymore. Take it out. That's it. Super simple. It also fit really well into the HTTP semantics, which are get and put. And all we need is to add a delete. Okay, so how does that fix the database problem? Well, effectively, a database was just a much more complex way of looking things up using a key. When you build a traditional database, you specify what your index is. Often they call it a key. So it really does act like a key, but it's multi-index. See, in a key value store, it's not multi-index. If you want multi-index, you build it on top. That's what file systems, what physical media file systems do. So we have all this stuff that we organize by inode number, for instance. Maybe you remember inodes from 313. Can't imagine Margot letting people escape 313 without talking about inodes, because he's a file system person. Me too. And that's it. It's just a key value store, and you put a namespace on top of it. The indexing, the directory structure, is on top. Simple idea. Very scalable. It can grow to very large sizes. The other nice thing about it is that we can split it up. So one of the ways we get scaling in a key value store is by putting pieces of it on different servers. Well, okay, that's great, but if we don't do that correctly, then what happens is if we lose one of those servers, we lose part of our database. Okay, but what have we been sitting here talking about? We've been sitting here talking about replication. So how about if I replicate some of the data? Let's say instead of having one server store, when we split it up, we call it sharding. You shatter it and you pick up the shards, the individual shards of the whole database. We could actually replicate the shards. What we're going to find is that, in fact, sometimes we don't necessarily want to do it that way. What we really want to do is create it so that we end up with a cover, but that each of the pieces in this cover that we build span multiple different shards. So in other words, our replication isn't one-to-one. We don't keep two copies of the shards. What we do is we keep, part of, so we take a big chunk of this database and we put this chunk on this server and an overlapping piece on this other server and an overlapping piece on this other server. And that actually will end up being what we implement. That's Project 5. How hard could that possibly be? Well, we're going to end up having to put a consensus protocol in there because we need to have some quorum here in order to know what we're actually doing, blah, blah, blah. And that's what motivates today's discussion. So the reason I'm harping on this is because Amazon built a key value store called Dynamo. Not to be confused with the database that they called Dynamo, because there's so few names in the world we have to recycle them. But in fact, Amazon Dynamo is a key value store. It wasn't the very first thing that Amazon Web Services released, but it was very early on. The very first thing that Amazon Web Services released was also a key value store, but they called it an object store. But it's pretty much the same thing, and that was S3, the simple storage service. And it was like about a year later, I think. Year, 18 months. It wasn't much later than this. This is really the incident that drove Amazon to create Amazon Web Services. They said, this is so cool, we should sell it to other people. The quotation here really drives home the fact that as you get more and more servers, you reach this point where even with low probability of failure, you end up experiencing failure all the time, and you have to become resilient to that. We cannot handle all failures, but what we'd really like to be able to do is handle common failures. So if we start off small, we say we're going to handle these failures. And then once we're comfortable with our solution for that, okay, it's working, now we can look at handling some of the other failures that we left to manual intervention before. And now we expand what we've done. And this is, in essence, what AWS has become. It has become this ever-evolving set of services that provides greater and greater guarantees to people who are using their stuff. And that was it. That's today's failure. And I liked it because there's almost no detail on really what all went wrong. Because at that point, they didn't have this culture of doing post-analysis and explaining what actually happened and whatnot. I was reading that yesterday there was an outage of YouTube that apparently was centered in upstate New York for some reason. Probably because there was a data center there and something went wrong in that data center. But we don't even have the analysis on that yet. So these kinds of failures happen all the time. There's a thing called the down detector. I don't know if you've ever used down detector. But in fact, when you're trying to use something and it's not working and you go look at down detector and you see the sudden spike of people reporting things are down, it's like it's a crowdsourced problem indicator. But we're going to be talking about quorum replication. The idea in quorum replication is we have two or more entities that make a decision on what the state of our database is. And for all intents and purposes, the only kind of database I'm going to think of as I'm going through this lecture is the key value store. Amazon Aurora uses, even today, quorum replication. Project 3 is a kind of choo-choo form of quorum replication. But like I said, start simple. Let's try to understand quorum replication before we try to get to Paxos. My goal here is really to make Paxos seem a lot easier when we get to it. The reality is, like, I was really surprised. Ivan doesn't really teach quorum replication. He just jumps right into Paxos. And I'm like, that's a really confusing way of doing it to me. This is 1979. And in fact, what's really weird is that when we go look at chain replication and crack, those are in the 2000s. So the idea of having a quorum is older than the idea of using chain replication. Chain replication was more about trying to make a particular model of quorum efficient. So part of what's going to become important here is to talk about consistency. So I'm going to go back and talk about consistency again. And then I'll actually get us into quorum replication. What happens when we just have writers? What happens when we have readers and writers? And then finally, I'm going to say, let's generalize this and go off the theoretical deep end and see how good we can possibly make our quorum replication. It's really easy for us to say, we're just simply going to use majority rules. Everybody votes, whoever has the majority wins. Can we do better than that? Remember, our goal isn't to elect a leader. Our goal is to maintain some level of service. And so I'm willing to let a minority work if I can come up with something that's viable. Primary backup replication is, in fact, a really simple model of quorum replication where there's one voting party. The primary is the quorum. We can think of that as the autocratic quorum replication. The primary is the leader there. And we have primary, backup. Primary fails, backup takes over. If the primary comes back, it's not the primary anymore. It's now just one more random server with an arbitrary state. Very simple quorum, but that is in fact quorum. And that is in fact exactly what Gifford taught us. Gifford said, you assign weights. He called them votes. He said, different nodes have different numbers of votes. In this particular system in primary backup, the primary has 1 vote and the backup has 0. If you want, we can make it better. We can give the primary 3 and the backup 1. Same outcome. Question? See, the view server is not actually the leader of the database. So it's not where we're getting the replication of the database from. The view server is solving a different problem, and that's the problem that's going to lead us into Paxos. And that is quorum replication relies transactional semantics. And you cannot get your transactional semantics if you have 2 of anything, or 4 of anything, or 6 of anything. Even numbers are not your friend. And that's because of our consistency model. And that's why we're going to talk about consistency again. In chain replication, what we really actually did was we gave the vote to the end of the chain. So it's still a quorum model, but it's the one vote that matters is at the end. And this is the way that it works in the real world, right? You work for a boss, and the boss is the one who actually counts. Your vote doesn't count for anything. Unless the boss isn't around, and then maybe your vote counts for a little tiny bit, and that could be enough. And same thing with crack. Crack was actually kind of interesting in that we gave some weight. We actually gave even weight to all of the participants except when we had polyvalues. When we had multiple potential outcomes, then all of the weight went to the last person in the chain. And that was because we were trying to make things scalable. So now this is where we get a readers and writers model. So you can see, in this case, we had readers and writers, and we had agents that were both. And the only one that counted in terms of writers was actually the one at the end of the chain. But in terms of readers, we could use any of the other readers as long as they weren't also writers. Because if they had 2 values, then we had a problem. We couldn't disambiguate that. A little bit of a stretch, but we could make it fit. So back to replication. What is a replica? Well, we have some client, because ultimately we are providing services to something, typically an application. Could be to other other services. And that happens a lot. That's why we've seen these failures where, oh, gee, XYZ service went down and that broke the ABC service and the DEF service and the PQR service, because they all relied on that. In that particular model, those other services were in fact clients. So we have some fundamental service we are providing to our clients. The client talks to one of the nodes, and then that one node works with the other nodes in order to provide the services necessary and to give us the guarantees that we need. Why in Project 3 do we not recover automatically when we have a primary and no backup? There's no recovery if the primary goes away there because we can't guarantee our services at the level we've promised to our client. We told our client, yeah, once we've told you something's happened, it's happened. It is durable. If I simply say, oh, well, sorry, the primary went away, I'm just going to go choose some other random server with some other random copy of the database, could be completely empty, and I'm going to make it the new primary, and now you're going to go and say, okay, get me that key, and you're going to, what? I don't have that key. And your client's going to be going, excuse me? You promised me this key. It's not a satisfying answer to say, I'm really sorry, but the service is down, but it's the only one that guarantees that someone's going to pay attention. If we lie and give the wrong information back, then things start to collapse. Bad things happen. So as bad as all these outages are, it's worse if we lie and pretend that we're giving you the data that you wanted and we're just making it up. Accomplishing this is difficult. So, we started with a simple primary backup model, and that's hunky-dory, but that still gives us, in this particular case, what is the point of failure here? What's the single point of failure we have to worry about? Our primary. In this picture, our primary, we didn't even build a backup model here. Now, we might be doing this kind of automatic backup so that someone can manually go in and swap the primary with the backup. It's the automation of that that's going to require our consensus algorithms. It's the automation that's going to require that we have some way of saying, okay, here's how we deal with it when the primary goes away. Project 3 does the choochie thing and it says, well, I'm going to use an external agent to make that decision. And part of that is because of the structure of Project 3. We kept it simple. It's really just, primary backup. And then some external agent that allows us to specify who's the primary and who's the backup. It's like a configuration server. That's what I really think of the view server as. It is, in fact, nothing more than a configuration server. This is a common model. When you go look at Zookeeper, when you go look at etcd, this is what these two big open source projects do. They are configuration servers. You're a client, you come up and you go, okay, I'm looking for the provider of this service. So we have some well-known name for the service, like a UUID. And I go to my configuration database and I say, yo, who am I supposed to talk to? That's our view server. It doesn't know anything about the service. It doesn't get itself involved in providing the services. It's just, how do I find the service? So we've kind of hand-waved the initialization problem off. We're going to have to deal with some of that. And it's never going to completely go away. You always have to have a location mechanism to find out where to go to get that service. And it'll have the same issues that we have with our database. Because guess what? Configuration databases are databases. They have the same possibility for failure. This is going to lead us into Paxos. Because our view server in Project 3 is this big, glaring single point of failure. If I can't find the configuration data, sorry, there's no service. Just a quick reminder, chain replication, we actually give all of the weight of the decision to the tail. The read requests go to the tail, the write requests go to the head, they propagate that direction. The only one that gets any votes here is, in fact, the tail. That's our quorum here. The tail gets all the weight. That's a simple solution. And in many cases, that's all you actually need. But we're not interested in the easy cases. We're interested in the hard cases, the really difficult cases. Remember crack. In that case, we actually allowed reads to be satisfied from any of the individual nodes, but writes, or when we had ambiguous reads, where we could be one of two values, the only way that we could arbitrate that was by going to the end. This is a more complex quorum kind of model. Basically, if there's only one possible value, then we know that that's it, it's quorum. And so now we have an example of where we can get quorum with less than 50% of the agents, because we've established a way to achieve that. So it is possible to do this. The disadvantages of replication are that when we have a primary, there becomes a single point of failure. We're going to have to deal with how do we get from a working primary to a non-working primary back to something that we can call the primary, even if it's one of the backup replicas. So we end up using the configuration database. I already mentioned this, blah, 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 tie it into project 3. How many of you have actually done anything on project 3 at this point? Hey, that's encouraging. It's like better than 80% of the class. And of course, none of the people on Twitch have actually raised their hands because they're still sleeping. Scalability is another downside to replication. Replication can kind of address scalability. That's one of the reasons that we built Crack, was because it gave us a nice scalable answer for read-heavy workloads. And you know why that mattered? Because 99% of actual workloads are read-heavy. But not all of them. There are write-heavy workloads. And there's enough write-heavy workloads that people are willing, and the people who have them are willing to pay lots of money, so we're going to solve that hard problem as well. Oh, and finally, there's the whole partition resistance problem, and that's really going to end up being what drives our quorum model. How do we deal with the network experiencing a failure? How do we make sure that we don't end up with two divergent copies of the database? You know, imagine that we took our view server and we replicated it, so we had two copies of the view server, and it gets split. And you know, we got the primary on one side and the backup on the other, and so we have two view servers. Now we think, so the one that inherited the backup promotes it to primary. Now you've got two primaries, and you've got clients talking to each of them. We have a problem. Because now we have a split personality. And we can't allow that if we expect to be able to automatically recover from it. Oh, we can do manual reconciliation, but we're not going to be able to do that in an automated fashion. I don't know if you ever used cloud storage. My favorite thing is that, of course, when you get a conflict, right, because an object has been modified by two different clients, and the cloud storage can't actually determine which one is the winner, like Dropbox will call it conflicted. I always end up deleting the conflicted copies, but that's not necessarily the right fix. Sometimes I have to actually look at them to figure out which one I really want to keep. All right, so I've talked about the CAP theorem a couple times. I'm going to dive into a little bit more here. One of the things we need to keep in mind is I've talked about consistency models, but I've talked about database-style consistency models. When we talk about the CAP theorem, the model of consistency we have here is not the same. Our strongest model of consistency here is, in fact, sequential consistency. We know the exact order in which events occurred. Why did I talk about distributed global logs? Because they give us sequential consistency across the distributed system. Availability. The service needs to be available to our clients. Now, sometimes our clients can get cut off from the service, and there's nothing we can do about that because we don't get to control the network. The network is this publicly available service that we use, but we don't get to quite control. And then we have partition tolerance. And this is really tied into how does the network actually fail? How are we going to deal with this problem? There's a dynamic tension between these three elements. The more we insist on consistency, the less we can provide availability. Because the dirty little secret here is that when Eric Brewer first formulated the CAP theorem, he was arguing that you can only satisfy two of them. And ultimately, what everyone has realized is that, no, you have to be able to handle partition no matter what. And the reason is because it isn't something you actually control. You get knobs where you can control how much consistency you provide or how little consistency you provide versus how much availability or how little availability, but you don't control the network, so you don't actually get to define how much partitionability you're going to handle. You either handle it or you don't. And it's externally dictated. And that's going to, in some ways, make the problem space a little easier to reason about, although it doesn't make it easier to necessarily fix in the real world. So let's be a little more formal here. Consistency here really means that we have a data item that we can only find one version of at any given time. No matter who I ask, I'm going to get the same answer. I don't actually care what the answers are under the covers as long as the system I'm asking. I do a get on a key, and I don't have the possibility of getting different answers. That's strong consistency. Availability means the failure of some node doesn't prevent the system from providing services to our clients. Our level of availability will depend upon the algorithms that we use. If I keep 100 copies of this thing and 99 of the copies go away, I can still potentially offer availability. I don't know if I can offer consistency and availability at the same time, though. Because if this is a partition situation where, boom, I partition the network, and I'm in the minority of one, and 99 things are in the majority of 99, and I start offering up my value to my clients, I may be giving them stale data. One of the interesting choices that Amazon made with Dynamo, their key value store, was they said, we don't want to be inconsistent, but we would prefer to be available. So we will take the risk that when things are melting down, we might give stale data out. Because availability, the website actually working when you go to amazon.ca, the availability is more important than the consistency. And this happens a lot in internet services, a lot. So we have these weaker consistency models. We compromise our consistency to guarantee higher levels of availability. And these are not binary conditions. We do not have consistency or don't have consistency. We do not just have availability or not have availability. We have variable amounts of them. So there's a much larger potential space of trade-offs here. What am I willing to tolerate? Partition tolerance. You have no choice. You have to be partition tolerant. Partition tolerance and consistency are tightly coupled because, as I said, if I have that example where I split things here and my one starts giving out stale data, well, that's not great. But it's better than, it may be better if availability is your number one goal. It may be better for you to give a stale piece of data than to refuse to service the client. What we don't want, and we almost never will allow if we can prevent it, is we don't want an update in both partitions because that will make consistency really hard to accomplish. So after Brewer actually formulated this, a couple of people who were much more theoretically bent sketched out a proof. they provided a formal proof of why the cap theorem is true, that you can only get 2 of the 3. And since P is always required, it's either you get C and P or you get A and P, but you don't get C, A, and P together. You can't have all 3. You cannot be partition tolerant and high availability and completely consistent. You have to compromise. The reason that we are here talking about this stuff is because how much you're willing to compromise will lead you to different systems that are useful for solving different problems. It would be so much easier if we could just come up with an absolutely perfect solution. But then they wouldn't need people like us to build distributed systems that work for all of these special different cases. This is job security. So here you go. If I have a partition of the network between 2 clients, and I have 2 copies of the database, and one of the clients reads from one copy of the database, and the other client writes the other copy of the database, I no longer have consistency. This is a simple demonstration of why partition, in this instance, leads us to an inconsistent state. Let's take a different approach. Let's say we are in this partitioned network and we have a client who can talk to database copy B but can't talk to A, and we're going to make them wait because A is the primary and B is the backup. Well, now the client doesn't get an answer. So we've sacrificed availability, haven't we? The service is no longer available. Maybe it's transient. Maybe we'll be able to recover from it. That would be great. Okay, let's do it where everybody talks to everybody else. What have we sacrificed this time? Well, you'll notice I had to take the partition out to get this to work. So that's great. So you can kind of see why we can't get all of these things in the same bucket. We're going to have to give up something here. And he's disagreeing with me. Great. All right. So his question, which is more of a statement looking for affirmation, is it looks like it's actually, project 3 is actually this case, the not available case. Let's see what the consensus here is. So how many people think that it is the not available case? Sorry, not enough votes for that, so we don't have a quorum. Done. So I don't know, it must be one of the other cases. All right, there were a bunch of people who thought that it wasn't that case, so I'm curious, for those of you who didn't raise your hands, why was it not an availability problem? Now this is fun, putting people on the spot who took the I'm not going to commit to an answer here and realized, oh crap, I committed to an answer by not answering. All right, I'm going to ask the question again. I'm going to ask for a consensus vote. How many people think that this is a sacrifice of availability in Project 3? Still, people won't commit. All right, there's a group here. I want one of you to tell me what you think we've sacrificed in Project 3. Did we sacrifice consistency, availability, or partitionability? Why? Why do you think it might be availability? Actually, I have already picked on you. I'll pick on you next. Oh, what do you think it is? I'm sorry? You think it's not partition tolerant? Do you agree? Yeah, the view server is the thing that screws this up a little bit, isn't it? Right. So in fact, the databases themselves are do suffer from availability problems, right? In that when the primary goes down, well, let's see. So the primary goes down. No, It's the partition case that's interesting. When we partition, anything that can see the backup but cannot see the primary can no longer make progress. So in fact, that's exactly this situation. The challenge, and I agree, that the complexity in analyzing this is we put this view server in there, and that view server is going to be the thorn in our paw for a while longer here. Because even in the documentation for Project 3, it says, yeah, the view server is kind of the single point of failure, blah, blah, blah. And I hand waved it off a little bit there when I said, well, yeah, this is part of configuration. But it is what's going to drive us to having more complex consensus protocols, because we have to be able to figure out how to deal with the failure of one of these nodes. And what we're going to end up doing is realizing that when we get a partition, there are going to be some clients who do not get service. We will sacrifice some level of availability in order to maintain consistency. So while I agree, I think that the most obvious analog here is availability, we have some complications in that analysis. So there, hedging your bets here paid off kind of, sort of. When you're actually building these systems, you won't be able to do that. You're actually going to have to think about this and say, what am I trying to guarantee? What's most important to my clients? What are the things that will cost this company money if I don't deliver them properly? That's what a service level agreement is. It's basically an agreement that says, this is what I guarantee you as my client in terms of usually availability. SLAs are mostly about availability. But they can also be about consistency, partition tolerance, we just have to do. No, what I'm saying is that if we have a partition and the primary is in one partition and the backup is in another partition, the clients in the partition that cannot see the other server, so if it's primary backup, what will happen is that the clients in the second partition will actually not get service. Now, in fact, what really happens here, this is what's interesting, and this is why adding the view server in here is a curiosity. If we really have a partition, we have a view server, we have a backup, we have a primary, and we get a partition, what do we know? Remember, the partition has to go through a line here, and there's only 3 lines. So pick one, right? There are 3 connections. There's a connection between the view server and the primary, the view server and the backup and the primary. Those are the only 3 connections that could possibly be broken. Pick one to break. View server primary breaks. So the view server and the backup can still talk to each other. What's going to happen? We replace the primary in the view server with the backup. And then the backup's going to nominate a new backup, and it's going to sync that. So now we're going to have a new primary, a new backup. And the people who are talking to the old primary, they get to talk to the old primary for a little while. Because I don't know if you remember, but the clients don't have to refresh their view very often, right? They have to refresh it periodically. So we are allowing some level of inconsistency, aren't we? Yeah, we are actually allowing a trade-off here. That's really good. Pick another line. The backup one goes away. Now it's the view server and the primary. What happens? Right, the view server is going to say, sorry, backup failed. And now the primary, so then the view server is going to pick a new server, and the primary is going to promote that. And the clients who can talk to the backup, they won't, actually, the clients don't talk to the backup, right? So in this particular case, it's fine. We don't even have any lack of availability there because the clients were talking to the primary in the first place. Maybe there was a primary that was on the network segment with the backup and they could have talked to it, but they won't know. So they won't talk to it at all. Okay, so we've survived that. Only one line left to pick. Anybody want to really go out on a limb and pick it? You already picked one. What's the one left? I mean, I'm giving you, this is a softball, right? You know, I'm very easy, over the plate, just got to hit it. What's the third line? So we're going to disconnect the view server, right? Because the view server can't talk to the primary or the backup. Now this is an interesting one because in fact, the clients will continue to work fine, the primary and the backup will continue to be perfectly happy to talk, and it's only the clients that try to get a new view and that fails that are going to end up going, I don't know what the state of the world is. And that's why the view server model in this particular project is a weakness in that it becomes a single point of failure. So we have sacrificed availability to fix a problem that's there because of the view server, right? We're using the view server to solve another problem, and we've created a new vulnerability. This happens a lot in distributed systems. So, partition is a property of the network. We don't really get to control that. Sorry, somebody else is wandering along and just casually pulling network cables and plugging them back in. I mean, anybody here ever used a wired Ethernet connection before? Sorry, I game, so you know what? It's wired. Wi-Fi sucks. It's less reliable. How's that? And anybody who's used UBC Wi-Fi knows it is less reliable. Consistency and availability are goals. And they are not binary goals. They are, in fact, a continuum. We may choose to disallow availability to some clients in order to have stronger consistency, or we may choose to have really weak consistency. We're going to call that eventual consistency. We're going to have this eventual consistency, and that means, the joke is, it means never consistent. And in fact, what it means is if we stopped everything and we let all of our systems recover, they would eventually reach the same conclusion. All of our databases would be in sync. But in the dynamic system, we may never actually achieve that level of consistency, which is fine, because eventually consistent systems are highly available. Sometimes you just get the wrong answer, but I gave you an answer, just like people in the class did when I asked them about Project 3. So the observation here is that some failure is better than complete failure. Project 3 is a perfect example of this. We have handled a class of failures. We no longer have a vulnerability on a single server when I have a backup that's kept in sync with the primary. And so I can handle the death of the primary and switch over to the backup. And I can do it fairly quickly. I mean, in the numbers that we have in that project, we're talking about, what, 100 milliseconds to detect that the primary is dead, and then however long it takes for us to synchronize the new primary with the new backup. That could take a while. Our job is to minimize the impact of those failures, to provide services whenever possible, and to manage the trade-offs between consistency and availability. And there's no one right answer. I know, you've just spent 4 years in school being told there's always a right answer, and here I am, I'm gonna scrape the rose coloring off of your glasses and say, sorry, that's not actually the way the world really works. The world doesn't have absolute perfect solutions, almost never. And in distributed systems, I'm willing to go out on a limb and say, never. Even trivial systems end up having complexities that you just never even imagine. This is all about consistency, so let's go over consistency models. We have strong consistency. There's only a single path through the distributed system. What is the problem with the strongly consistent distributed system model? Two hands at once. Okay. You can answer it and then we'll take our question. But I was just looking at consistency right now. I understand you're talking about availability, but I'm just talking about consistency right here. How do you achieve a single path through a distributed system? Yeah, you've just touched it. It has to be perfectly sequential. And how do you make things perfectly sequential? You do one thing at a time. What is the problem with doing one thing at a time in a group of 100 different nodes? It's slow. Who's going to pay you lots of money to take 100 machines and make them run as fast as one? Or slower than one? Now your question. No, it's actually stronger. Actually, yes, it is sequential. Yes, it is sequential consistency. I'm sorry, I'll take that back. Yes. So we don't actually need this. We spent a lot of time earlier talking about consistency and how we can have equivalent paths. And so when we do reconstruction, all we need is a consistent cut, because that will get us a potential path through the system that leads to the same outcome. So we don't actually care about the strong consistency. We're not willing to pay the slowdown cost of strong consistency almost ever. Except, of course, when we're debugging, that's what we want. You can use logs to achieve sequential consistency, yes. The problem is that what you end up with normally is, unless you're using that global common log model like we did with Corfu, you will end up with a path through the system, but not necessarily the path through the system. No, a path through the system. The path through the system means there's only one path. A path through the system means there are different paths that lead to the same outcome. That is single consistency, yes. Strong consistency, there's only one path. Single consistency is there's a path. There are potentially multiple paths that are equivalent, and we just use one of them to reason about. Strong consistency, and see, now we're moving back and forth between terminology domains, and I realize that's making it confusing. Right, so strong consistency is a single path through the system. There's no other paths to choose from. That is, I don't know, I'm gonna have to go back and look and see how I define sequential consistency to make sure that I'm saying this right. There's so many different consistency models, sometimes it gets a little confusing, which is why I wrote them down again here, just to make it even more confusing. So I'm gonna stick with what I say on the slide now, and I'll reserve the right to amend later. And now you can see why it's hard to be consistent about consistency. Causal consistency only guarantees, and causal consistency is actually the interesting one. It only guarantees the ordering of causally related changes, and it says nothing about the ordering of unrelated changes. You change a field in a database, I change a different field in a database. They're not causally related. You didn't see my value, I didn't see your value. The order in which they occurred is not defined. That's actually the consistency model we're going to see in most of the systems we really analyze. Not the stronger consistency models that we like to see when we have logs, for instance. So a causal consistency means that we're going to have strong consistency or single consistency for causally related events. But for non-causally related events, we have weak consistency. We don't know exactly the order in which those things occurred. And it shouldn't matter, assuming we wrote the code right. Small details. Eventual consistency is even weaker. It basically says that we could recover the system at some point and get to a stronger consistency model, even though in the dynamic system, as it's running, we don't achieve that level of guarantee. So if things crash, we can get back to an actual consistent state. We can give you strong consistency, either causal or single or strong. But while the system's dynamically running and eventually consistent, well, you might see some weird stuff going on, but that's okay. Eventually we'll fix it for you. Eventual consistency is in fact a very common model because it provides us with high availability, a reasonable level of consistency that we can usually live with, but the possibility that occasionally we are going to use inconsistent data because we aren't actually looking at a consistent state at this moment in time. If I'm pulling things out of inventory because I'm selling them, I might be willing to overcommit. And then when you actually try to buy it is when I actually try to make it consistent. And I actually tell you, I'm sorry, that item is no longer available. There was a question. There were two hands over here. So he's already asked one, so I'll, it's better to give an answer than it's better to give a wrong answer than to give no answer at all. How's that for a kind of weird way of thinking about it? It was right recently. It's just not right. It may not be right now. No, actually, when we restore, we will give a consistent answer. It's in fact only while we're running that we will give potentially an inconsistent answer, i.e. we will give an answer that is not visible to everyone in the system. Remember, the original consistency here was there's only a single version of a given key. So whoever does a get on that key gets a particular value back. As we weaken that consistency model, the answer is if you guys both issue a get at the same time, you might get a different answer than he gets. You could even ask the same question. You could say, get me that key twice in a row, and it could change. The interesting thing there is that you can't necessarily know whether or not it changed because something happened between your gets. S3 is weird in that it will give you old versions potentially. And you have to understand that. So the consistency model isn't strong consistency. It is a weak consistency. It says, I will give you an answer, but that answer might be yesterday's answer. So if you want to know what that answer was, you're going to have some additional mechanism on top of that to reason about what you're looking at. I mean, in fact, I think I mentioned this, is that in S3, the best thing to do is to never rewrite a key. So if you take away mutability, a lot of these problems go away as well. And this is actually why eventually consistent systems tend to work pretty well, because a lot of times we generate things and we never change them. So you grab a web object. We're loading things into a web page. You grab a web object. The web object that you're grabbing is not actually from the database. It is from a content distribution network node that has cached a copy of that and hands it to you. Why do I do that? Because it's way faster. So that improves my availability. If someone changed that key in the database, it will take a while for the CDN in the cache to notice that it has changed. So I'm going to be handing you stale data for a while. Read mostly workloads work really well with eventual consistency because they optimize performance at the risk that once in a while we're going to give you a stale version of the data. And that's considered to be an acceptable trade-off. I mean, my gosh, the wrong icon could appear on your web page. How horrible would that be? Worst part is when you're rendering a web page, sometimes you actually have to have the object in order to figure out what the size of it is, because when you do the HTTP query to get the size of the object, it doesn't tell you. And so you don't know how big to leave the hole. Because otherwise, if you can just get the size, you can leave a hole there and put it in later. But if you don't have that, it's a guess. And that's why you see pages where the ad covers the text. Oops, you told me that was this size and you gave me an object of that size. And of course, those web browsers don't actually clip the object, which is what I think I would do if I were doing that. But advertising pays their salaries. Now we get to quorum replication. This isn't the language that Gifford quite uses. I'm using the language of weighting. Gifford uses, his weighting is done in quantized votes, and it doesn't make any difference. It leads to exactly the same analysis. and that is every node in the system is now given a status as a reader or a writer, and it gets a weight related to its how important it is. And so the idea is that if I want a consistent view of an object in a state, in a system where there are multiple copies of the object, I have to read from enough of these locations. So not all of them are mutable. Writers are mutable. In fact, you can read from a writer as well. All of them will have some copy of the object, or they won't have the object, in which case you will get an error back. As long as you can read from a majority, based on the number of votes they have, based on their weight, you know that you have the consistent copy of that object. And this is kind of cool, because now we've gotten ourselves out of the, oh my gosh, I have 100 copies of this object. Do I have to read all 100 of them to know that they're consistent? And the answer is, well, no. If I can read from 51, if I have 100 votes in the system and I can get 51 of them, then I know that I have the definitive copy. The other 49 could have a different value. But as long as everyone follows the voting protocol here, they will always get a consistent copy. Now, the reality is, when we build our system, the client doesn't talk to all 100 copies. The client talks to some front end. The front end then talks to the 100 copies. Or it talks to the subset of 100 copies. Now, 100 is a terrible number. The really interesting thing here is that the right number is almost always 3. As you put more in there, it gets more expensive to maintain the copies. But there are times when you're going to want to have more than 3. Not because we want more than 3 in a data center, but because we want to have multiple data centers involved. And so usually what will end up happening is we'll put copies in other data centers too. You might go to more than 3 because of scalability. It's very rare in the real world to actually go in a single data center to go above 3, because it almost never provides you any additional benefit. And I'm hedging here, because when we start sharding things, all bets are off. But in that case, what we're going to want to do is we're basically going to want to have a version of our data on 3 servers. That's going to be kind of our ideal sort of sharding model to start off with. And as you learn more about your system, you might decide that you want to have more availability than that. Because remember, with 3, the reason that that works is that you only need 2. So the whole point of this, and I actually think Gifford's paper is very easy to read, which is why I said you really should read it. The whole point of this is he did it on top of file systems. He didn't do it on top of databases. He did it on files, and he talked about weighting, and he talked about replicating the data and whatnot. And it was really cool because he had an ability to have both read-only copies and read-write copies. In 1979, he's doing this, and it made a lot of sense. It really made a big difference. And his suggestion, which I agree, is that use version numbers if you want to determine which copies are current. You just have a monotonically. Gee, look, we're back to Lamport clocks again. A monotonically increasing value, a version number. Previously, we called them segment numbers. They're all Lamport clocks. Quorum replication is nice because it means that it will work even if some number of the copies are inaccessible. So now we actually are addressing real kinds of partitioning here. We can build this on top of a transactional storage layer. He was very happy about this, right? So in fact, you can build this kind of quorum on top of a transactional system and get correct transactional semantics without having to require that everyone who has a copy be updated properly. Now that's part of your protocol, right? Because if you are a copy and you fall out of the quorum, you're going to have to restore your consistency at some point, and that's going to be a separate mechanism. But that's not important to the quorum model. It does actually provide strong consistency. And when you build strongly consistent systems, this is in fact what we're going to use. We're going to use quorum models. When we move to Paxos, the interesting part about Paxos is we're going to have a flexible leader election, because underlying all of this quorum stuff is we still need a transactional system to give us the kind of semantics we require to mutate the state in a consistent fashion. And if we have a leader, then we have a point of vulnerability. So we are going to need to address the problem of the leader becoming unavailable. It's Project 3's view server issue. How are we going to minimize our dependence on that? And the nice thing about using weights is that you can adjust things out to give different weights depending on whether your goal is availability or consistency. I actually stole this picture from one of the papers, one of the recommended papers that was talking about all the different kinds of consistency mechanisms. You know, you have read one, write all, which is an interesting consistency model. It's very high availability with high consistency. So you have to write all the copies, but you can read any of them. And you can see how that becomes a quorum model. Yeah, okay. So the reader has 50% of the votes, and the writers each have their tiny sliver. Oh, is that right? I don't know. I have to add that up correctly. So you need all of the writers plus one reader in order to have a quorum, and that gives you your consistency. Majority consensus models. That means we can have some nodes that are out. Fine, not a problem. Grid protocols are going to be interesting because I'm going to talk about crumbling walls, and crumbling walls is an extension of grid. And the reason they called it crumbling walls is because they don't actually have a strict grid. That's where it becomes kind of interesting. And it's sort of what happens like when you have multiple data centers. And I'll get to that in a minute. And lots and lots of these different ways. These are all different versions of quorum consensus protocols. They all came after Gifford's work. I think TQP came out contemporaneously. This is a systems class, so of course we're going to take the systems paper over the theory paper. Primary backup is a really choo-choo version of consensus, where the consensus is the primary has all the votes. Very easy to reason about, though. Even if we have two backups, same thing. Primary's got all the votes. The way that we deal with failure in this is through the configuration approach, where we change who the primary is, but the new primary now gets all the votes. The backups are just there to take over in case the primary is eliminated. Okay, so what do we do when we have, oh, the title's wrong. We have a reader and a writer. How do we assign our weights here? Now, see, the interesting trick here is that what we've done is we've said that there's a transactional system between the two databases that are keeping it consistent. So in fact, it doesn't matter. As long as we weight them the same, we'd end up with a consensus. Why would we maybe give more weight to one copy than the other? Maybe we want to prefer readers over writers. I don't know. There was a question in the back. You can do it either way, actually, right? So in fact, in this case, these are only one of those actually accepts writes. That's why this is kind of a fake example. It's not a great example of it, but in our instance, the primary is serving as the front end for the clients. The clients only use the view server to find the primary. So the view server isn't quite isn't a participant in maintaining the database consistency, and you only talk to the primary. But remember when we went to crack and we went to chain replication, we ended up reading off of effectively the backup copies, not the primary copies. So you did writes to the primary and the reads out the end, the backup at the end of the chain. And then when we get into crack is when it becomes interesting because we end up, it's like, how would I deal with these poly values in terms of weighting? How would I describe that as weights? And I know I can describe that as weights, but effectively what I'm saying is if I have two values, I kind of have zero weight. That only the guy at the end who has a definitive answer has all the weight. And so it sort of devolves down to that. But I only care about that when I end up with a collision. And so that's why those aren't very good quorum replication examples. We can fit them into the model if we want to, but they always end up turning into these degenerate cases where we have one entity that gives an answer. Crack is more interesting in that we actually will allow us to do reads, and that's nice because that's more like write all, read one. The example here, read one, write all, where I write all of the copies, but I can read any of them. Absolutely. Weights can be dynamically adjusted. Absolutely. There's nothing that requires the weight be static. So our choice of weights here will probably depend upon exactly what we're doing. What happens when we have multiple writers? See, this is interesting because I just took the 2 database example and now I've turned it into 3. And I told you 3 is a nice number to work with. I would just give them the same weight. And the reason for that is because the only way you get a majority there is to have 2 of them available. And that gives me my partition tolerance, and it gives me the best availability I'm going to get. What happens when I introduce readers and writers? This is kind of an interesting one. What is the right weight? I just said, and I spent some time while I was drawing this slide, and I'm going, well, actually, it kind of doesn't matter, does it? In fact, the answer is it depends on what I'm trying to provide here. If I'm trying to provide high availability, I'll probably give readers at least as much weight as I give writers. If I'm looking for stronger consistency, I'll probably give writers more weight than readers. As we were talking about, I might dynamically adjust these weights depending upon the needs of my particular system. And Gifford ends up noting that manipulating these allows you to change the performance and reliability of the underlying system. This is the reason that we would change the weights. There has to be some set of the readers and writers that have the same value. That's all quorum consensus is. I mean, I can talk about all these weights and whatnot, but in the end, we vote and we look at the values, and if we can form a majority of the voters that all have the same value, then we have a consensus. The minority loses. The majority wins. And we're out of time, so there's probably like 5 minutes. I'll go back and do my usual thing of recording it so that no one will watch it. Does anybody watch the... Couple people. Yeah, they're not that long usually. It's only 5 to 15 minutes. But this is a really interesting example. I really like this paper, and I haven't seen anybody else talk about it much. But what's really cool about it is it gives you a model of consensus that doesn't require a majority. It requires a very carefully crafted plurality. And the picture here is useful in that it's telling you you need to own all of the nodes in one row and one of the nodes in each of the rows for that that match the one in each column that has a corresponding entry in the row. And that's like one data center has all of the stuff, and then all of the other data centers, at least there's one node there that has a copy of it. So I'll talk through that a little bit more. And that will be it for today.